we can better predict when they're going to take place and prepare for their human health impacts and the associated economic impacts that might occur. And so today I thought it would be helpful to sort of give you really a broad overview of climate science overall, moving from the very beginning of Earth out into what we see today and what we might project for the future. And so we'll start out with this understanding of the physical science of climate science so we can get a bit of background for some of the terms that I'm going to use today. So that's where we'll start in the next couple of minutes. So the first thing I want to do is really provide a description of what the difference is between weather and climate. And so specifically, we can think of this as the difference between what we get versus what we expect. And so weather is the what we get. It's really this day-to-day variation in the atmospheric conditions such as temperature, precipitation, or wind. And so in this little call-out box, I've provided an example of sort of a weather station reading from Ridgewood from the last week, where we can see whether it's going to be sunny or whether it's going to be rainy, what temperature we're going to observe in the morning and nighttime, as well as how much precipitation might fall if it does. And so we can also see this an example of weather patterns in these sort of math presentations. And so we can see we have these cold fronts coming in, we have precipitation indicated, we have these low and high pressure systems, all of which fluctuate throughout the day over the hours. And so these very short time scales. In contrast, climate is really what we expect. And so it's the atmospheric conditions at a specific location at a given time of the year. And so this is really just the average of the weather conditions that we see from day to day. So on the right-hand side, we have this image that kind of illustrates all of the different components of our climate system. And as you can tell, there's a lot of arrows, and so it's a pretty complex system. Specifically, we have the input of radiation from the sun, so the warming effect that has. We have the atmosphere and the different gases that make that up. We have these clouds, which are bringing down precipitation, but they're also serving either to cool us or warm us, depending where they are. And so all of these things work together to create a pretty reliable system that acts in a predictable way. And that really is our climate and the way we can understand it in contrast to the weather systems. So an example of this we can take from LaGuardia Airport data that has been collected over the past couple of years. So in this graph, we have an example year from 2005, and we're looking at the month of January. And so it's just plotting the degrees temperature. Specifically, first we'll look at sort of the day-to-day variation. So if we look at this dark blue and this purple color, this is indicating the recorded temperatures at the highest temperatures of the day and the lowest temperatures of the day. And you can see that at the beginning of the month, it starts out pretty warm, actually. It's about 60 degrees at the maximum, and then it drops down over the next few days with some blips in between, and we see this big peak at the 15th, and then back down, but it's bouncing around quite a bit. And in contrast, we also have this normal max and normal min plotted. And so this is really an average of all the conditions that we would expect during the month of January over the past 30 years or so. And so this really provides us with an idea of what the climate looks like. So it's what we would expect from these specific days. If you wanted to know the average temperature on January 17th in a given year, you would look at what this average looks like. And so while this provides an idea of what we expect of what the climate looks like, these specific variations on a day-to-day scale provide us with the weather, or what we get. And so those distinctions are really important. The next definition that I want to go through, now that we understand what the distinction between weather and climate is the difference between climate variability and climate change. So specifically, climate variability is going to indicate the short-term fluctuations in our climate, while climate change is going to describe the long-term and persistent change that we observe. And so climate variability can really take place on timescales that's about season to season or decade to decade. And an example of this would be El Nino or La Nina conditions. So you may have heard this term before. And we're actually in a La Nina condition right now. That's been confirmed as of this fall, that we're in sort of this La Nina state. And so what does that mean? If we take a look at the graph on the left-hand side, we see these big maps of the world's oceans, and the red colors are going to indicate temperatures that are higher than normal, while the blue colors are going to indicate temperatures that are colder than normal. And so what this is telling us is that we've named these situations where the this is the Pacific Ocean, where when the water around the equator in the Pacific is warm, we call it El Nino. And when it's colder than normal, we call it La Nina. And so we're in this La Nina state right now. And this fluctuates every couple years, I would say. And this is a very specific pattern. To talk about this one sliver of ocean in the Pacific Ocean seems really specific, but it actually has a lot of implications on the climate around the world. And so specifically, we can look at this graph on the right to see how this influences both precipitation patterns and temperature patterns that we might observe. And so specifically, a thing that I think is interesting is that during La Nina conditions, in the winter time, we tend to see drier conditions in the south part of the United States. And so this is something that's really important for us to take into account when we think about things like wildfire season. As we have probably seen in the news recently, the wildfire season in California this year has been really intense. And so this doesn't necessarily tell us that La Nina made those fires more intense, but it tells us that all of the conditions that are necessary for those fires to be really easy to ignite are present when this type of condition is taking place. And so these types of climate variability are really essential. They're things that we can predict pretty well. And we're really interested in understanding the global influences of these types of variability. In contrast, climate change is this really long-term and persistent change that happens to our average weather patterns. And this can be caused by both natural factors and human activities. So this graph on the right is one of the most classic examples of a climate change graph that you might see in the study of climate science. And so what this is depicting is we have on the x-axis increasing in time from the 1960s to the present. And on the y-axis, we have the concentration of carbon dioxide in our atmosphere, which is a known greenhouse gas. So what we can see pretty clearly is that over time, there's been this dramatic increase in carbon dioxide in our atmosphere. And it's steadily increasing. There aren't too many fluctuations. We have these very small blips, which turn out to be dependent upon the seasonal cycle. But overall, we have a very strong increase over time. And so this is the kind of thing that we're describing when we talk about climate change, when there's a lasting and persistent change in the way that our climate looks. And so this is also when we think about the word climate, what we think about what we're hearing from the media. And so on the left-hand side, we have all these examples of recent literature coming out in popular media that's talking about how greenhouse gases need to be cut in terms of our agricultural production, how climate change may also be making wildfires more intense, how the hurricane activity from this season might have been more intense because of climate change, and similarly impacts on other weather disasters. And so when we're talking about these different natural phenomena, it's really important that we separate out the influence of climate change and climate variability, and we understand how they can really act together to have really resounding impacts on our climate system. The last thing that I want to talk about in terms of definitions is the greenhouse effect. And I think that this one's interesting because when we think about all the negative impacts of climate change that you might have heard about or you might be talking about with your friends, we think of the greenhouse effect as being this really negative, scary thing. And the fact is that actually it's a very special phenomena that really keeps Earth within this Goldilocks zone. It's not too cold and it's not too hot, and it's the perfect environment for humans to exist on our planet. And so specifically what the greenhouse effect is doing is it's simply referring to the fact that specific gases trap heat from the sun and keep Earth at a warmer temperature than it would be without those gases present. So some example of these gases are carbon dioxide, that's perhaps the one that you've heard the most about, but also methane, nitrous oxide, CFCs, and even water vapor. And so these all act together to form a sort of blanket around the Earth. And so you can see in this little schematic that the energy is coming in from the sun. So just like you feel warm as you stand in the sunlight, all of that's coming into Earth and serving to warm up our planet. Some of that is going to bounce straight off and go back into space, but some of that is going to be trapped in our atmosphere and radiated back down towards the surface of our planet. And that's actually really good because on average, the temperature of our planet is about 60 degrees Fahrenheit. And we think about that, I think that that sounds pretty comfortable. You know, it's a little chilly. It's probably a little cooler than we would have our houses set out, but it's definitely something that humans can survive in. And in contrast, if we had no atmosphere, no greenhouse gases in our atmosphere, the surface of our planet would only be about 0 degrees Fahrenheit. So that's well below freezing. And that would have a lot of negative impacts on, you know, whether or not humans could exist on this planet. And so in itself, the greenhouse effect is a really essential element of our climate system, and it's what allows us to live comfortably on our planet. The key here is that the more and more of these greenhouse gases that we add to the atmosphere is like adding layer upon layer of those heavy blankets onto our climate system. And that's what's triggering this climate change, which has a lot of associated negative impacts, which we'll talk a little bit more about later in this presentation. So now that I think we have a good basis in the physical science of climate, let's talk a little bit about how Earth's climate has looked in its past history. So I think this is an interesting question because we think about, checking the weather if we need a jacket, or checking the weather if we want to see if it's raining outside. And we know that we have these really great weather systems today. They record all of the different changes from day to day. But how did we possibly do that so far in the past if we only recently started taking weather data in the way that we think of it as today? Luckily, we have these things that we call climate proxies, and this allows us to really indirectly reconstruct past climates on Earth. And so some examples of what we use as proxies are ice cores, tree rings, and sediment cores. So ice cores come from these really deep layers of ice up in Antarctica or Greenland, and if you can kind of see it in these images, they trap a lot of different things within them. And so specifically, you can have these little gas bubbles, or you can have specific chemical concentrations, or even pollen from plants that are trapped within each of these layers. And what that's going to tell you is what the atmosphere looked like if you can literally preserve that atmospheric bubble from the time during which the ice was created. You can tell a lot about what the Earth used to look like in the distant past. And similarly, we have things like tree rings, which can be used to determine more recent past. And so you might have learned in school growing up that these tree rings indicate each year that of the growing season for this specific tree. And so each of those can be counted to determine the age. And the thickness of each ring can really be used to infer fluctuations in things like temperature or precipitation, which will affect how efficiently the tree is going to grow. You can also see things like scarring or sort of like burning conditions that are going to indicate things like wildfires as well. And so this is a really helpful tool for the more recent past and for looking at Earth's climate history. And then third, we have these examples of sediment cores. And sediment cores can come from both land or ocean. And this is really just looking at deep soil or deep down in the dirt and looking at the different chemical compositions and the different layers that make up those sediment cores. And so we can learn things like if there's charcoal found, it indicates that fire has taken place. And if there's specific sort of critters that were swimming in the ocean hundreds of thousands of years ago, we're able to see sort of the chemical composition of the shells that they had made or their skeletons. And we're able to infer different compositions of our atmosphere or of the ocean that go along with that. So these are really helpful tools in terms of reconstructing quantitative measurements of Earth's climate history. And so we see an example of that in this graph in the center. Here we can see how far back we can really go with these types of proxies. And so on the x-axis, we have the present in year 0, or a little bit before the present, probably about 1950, all the way back to 800,000 years ago. And so we have plotted here both the temperature change and compared to present. So a -9 would be about 9 degrees Celsius colder than it is today, as well as the changes in carbon dioxide concentrations. We can see that there's pretty good tracking between these two metrics. So between the carbon dioxide concentrations and the temperature, which indicates what we talked about previously, that the more CO2 we have in the atmosphere, the more warming we're going to experience due to the greenhouse effect. And so I think it's pretty interesting to call out how many different times we move from peaks to valleys. And so there's quite a few different swings in this data, and they're pretty dramatic in terms of the amount of temperature and carbon dioxide that they're changing between. And so this begs the question of what causes these really distinct changes. Well, there are a source of very natural climate change within our climate system. And one example of this is the changes to Earth's orbital cycles. And so some of these are named the Milankovitch cycles after a famous geophysicist. And I think these animations are really helpful from NASA, and they are pointing out how changes in Earth's orbital cycles can affect the climate that's experienced on Earth. So specifically this first one is changes to the orbital shape. So Earth doesn't orbit Sun around in an exact circle. It's really more of an ellipse or a stretched out oval. And that oval shape actually changes over time. And so specifically it stretches out a little bit and then it returns back to closer to a perfect circle than before. And so this changes from the largest value down to the closest value in about 100,000 year cycles. And so you can imagine that the closer Earth is overall to the Sun, the stronger the sunlight that's felt on the Earth's surface and the stronger the radiation that gets felt. And the farther away is sort of the opposite. We see another different change and an example of sort of the way that the Earth is tilted. And so as the Earth, we have these large orbits around the Sun, but we also have a rotation around Earth's own axis. And so that's the difference between around the Sun is this movement in a year versus around its own axis is the movement that we see in a day. And so this rotation about Earth's own axis is actually tilted. So it's not exactly perpendicular to the orbit that it takes. And this tilt changing can also have a significant influence. So it's only changing about 2 degrees. So this tiny little wiggle in the tilt is not very extreme, but it does have an intense impact on the amount of radiation that's coming in towards the top of the Earth versus at the lower latitudes. And similarly, we have this sort of wobble of the orientation of Earth's axis. And so this is also going to impact which part of Earth is tilted towards the Sun at what time. And so those kind of changes are on the order of tens of thousands of years. Other natural sources of climate change include changes to the Sun. So you can have things here like sunspots, as well as solar flares, which are going to increase the amount of radiation that's coming down to Earth's surface, as well as things like volcanic eruptions. And so you can see from this example with Mount St. Helens of this really dramatic outgassing that occurs during a volcanic eruption. And so that's going to pump all of these different gases into the atmosphere, but you can also see these particles that are quite dramatic. And so these particles help to create clouds. They essentially provide a surface for clouds to form more easily. And so as you can kind of expect, if the clouds are high up, the effect that, if they're low down to the ground, the effect that that's going to have is going to be cooling. So just like if you're out in the sun, totally exposed to the sun, it feels very warm. And as soon as you feel a cloud pass over you, it's going to be cooling. And so that can also have sort of a natural effect on Earth's climate. So as we think about all of these natural ways that Earth's climate has changed throughout the past, we want to know how that can inform what our climate looks like today and how it got there. And so we come back to this similar graph. Here now we're just plotting the CO2 fluctuations, but now we've extended it. So previously we were just out to 1950, and now we've extended it out to year 2020. And so this is sort of the current time. And so the last records that were available were that on October 25th of this year, we observed a total concentration of about 411 parts per million. And so this is quite different than this average of about 200 in the 200s or mid 200s that we had seen throughout Earth's history. And so what could be causing that very sharp increase? The first thing that we could think about is like, well, what is it natural? Are any of these systems that we saw at play throughout Earth's history, what's influencing our climate now? And so let's think about the orbital cycles. Could it possibly be that this sharp spike I have reproduced down at the bottom could be caused by the changes associated with the orbital cycles? Well, no, this is only taking place in about 70 years at most, whereas we saw that the orbital cycle changes were on the order of tens of thousands of years or 100,000 years. So let's move on to the next one. If it's not orbital cycles, could it be the solar variation? So could we see sunspots or solar flares that are causing more solar radiation to come down to Earth? It turns out that radiation from the sun has actually been decreasing over the past few decades. And so we would actually expect the CO2 trend or specifically the temperature trend to be decreasing, whereas we see that it's dramatically increasing. Similarly, what about volcanic eruptions? Could those have been increasing the dramatic temperature warming we're seeing in the past couple of years? No, as we saw from the previous example, these volcanic eruptions would lead to a net cooling effect. And so that, again, does not match the temperature change that we've seen in the past decades. And so luckily, we can use climate models today to really separate out the effects of the natural forces and the forces that we are adding from human effects. And so in this graph on the right, or on the left, we have on the x-axis time over the last century or so. And then we have the Earth's average temperature in degrees Fahrenheit. And so we see this dark black line is looking at the observations. So what do we actually see in the recorded temperatures changing over the past century? And so we see this projected increase, as we would assume from based on the data. And so what if we were to isolate only the natural forcing? So all of those things we talked about before, there are also additional forcings that are coming about naturally. What if we only plugged those into the climate model? What would the world look like? In that scenario, we don't really see any increase. It's pretty flat. And if anything, over the last 50 years, we see a bit of a dip in the temperature. In contrast, if we're to add the human effects back in, so the amount of greenhouse gases that we are physically putting into the atmosphere on our own accord, we do see this sharp increase in the amount of warming that's observed, specifically starting in about 1950. And we see that this also tracks our observations quite well. And so I think our only really understanding that we can take from this graph is that humans really are the culprits. And so we've observed already quite a few influences and impacts that are associated with this net warming. For example, we've seen that we have sort of longer heat waves. So this is an example from Austin, Texas, and we see that the longest streak above 100 degrees Fahrenheit has increased in length by about 15 days since 1970 to the present. And there are some more indirect impacts that we might see as well. And so things like mosquito days. And so this is based on the idea that mosquitoes can only really live in these very specific temperature conditions. And so if we're to increase the temperature of our planet, they're able to survive in a longer time period. And so in San Francisco, for example, we're seeing almost a month longer span of time during which mosquito season might take place in terms of changes from the 1980s to the 2010s. Further, as we discussed before, a lot of the wildfire variability might be caused by sort of internal variability or natural variability on our planet. But we can also see some very clear trends in terms of if we look at the net temperature increase of our planet over the span from the 1980s to 2010s, compared to the amount of acres that are burned in the Western wildfires. And so this suggests that there's impacts in terms of wildfire risk as well. And so if these changes have already been observed over the past 40 or so years, what might we expect from the future? And so that brings us to the last section of this presentation, is what are we looking towards over the next century, and really what can we do to help? And so luckily, climate models help us answer a lot of these questions. And so what climate models really do is they take this entire Earth and they break it down into what we call little grid cells. And so it looks really similar to the way that we used to do math on that grid paper, with every little square representing sort of a set of equations and processes. And so you can see that we have both squares on the horizontal scale. And so this is really covering the surface of the Earth, as well as this vertical scale. It's a little harder to see, but that's really emphasizing the amount that we're able to model the atmosphere and how high up on the planet we're interested in. And so within each of these little boxes, we have that whole complex climate system. And so each of these systems are really linked in this physics-based representation, and we solve a host of different equations to understand how each of these components of the climate system influence each other. And so this allows us to link processes between the atmosphere, between the ocean, and the land. And so we can get pretty complex processes that are modeled just using math and physics. The key to this is that that's quite a lot of calculations. There's a lot of equations that are going into each of those grid boxes, and that requires a lot of computing power. And so what we tend to use are supercomputers, or what's called parallel computing. So essentially running a host of different analyses and sort of executions of these equations at the same time. And so this is an example of a supercomputing resource or a group of supercomputers. And it really just, I think it looks kind of silly, honestly. It reminds me so much of just what your hard drive looks like on your big desktop computer, all stacked together in this giant room. And so that's really what's necessary in order to run these global climate models and resolve all of these very small scale processes. And the benefit is that as our computing power increases, we're able to make our models more and more complex. So you can see in the difference between this first graph, where we have what climate models may have looked like in the 1990s. It's very coarse. You can't really capture, I couldn't even really guess what this region might be. And in contrast, in even 2007, so 13 years ago, which is quite a long time in terms of how quickly computers progress, we see how much more detail we can get out of this little plot of the climate model. And so I like to think about it in terms of how fast you've seen perhaps your flip phone convert into what we have as smartphones today. The amount of computing power that's in our pockets is so much more than it was even 10 years ago. And that applies to the way that we run climate models as well. And so there are many limiting factors in terms of how much better we can improve this resolution. But on the whole, increasing our computer power does have a lot of benefits in terms of making our models better. And so this allows us to create these projections over through the end of the century. And what we see is that there's quite a range of projections in the future temperature of our planet. And so specifically on the left, I have this figure that's outlining a set of two different projections for what we might see by the end of the century. And you can see that one is quite a bit lower than the other. And so part of this, in terms of sort of the spread of these values, we see that the dark lines in both of these examples are indicating the average of all of these different, what we call model realizations. And what that's just saying is that we put in a bunch of different initial conditions or slightly different starting points and see how different the climate can be by the end of the century. And this allows us to be really sensitive in all of the things that we're taking into account in the models and make sure that, if something's not quite right, we're capturing all of the range of possibilities. And so that gives us this shaded region is sort of the minimum and maximum of those types of models. But in contrast, we have these two different scenarios that are called out. And the difference between this is really human choice. And so this lowest scenario, which we call the representative concentration pathway 2.6, is just the difference between, that's really a scenario in which we cut all of our emissions as soon as possible. We take everything we can, we reinvigorate our electricity sector, we change our transportation methods. Everything is really as aggressive as we can in terms of curbing our emissions and stopping climate change. And in contrast, this taller and higher projection is associated with what we call a business as usual scenario. And so we like to use that term to really describe what would be the case if we just completely ignored all of the things that we know are important about preserving our climate, and we just carried on the way we are today. Industry grows on the trajectory it's on already, and we really don't make any efforts. And so this big difference between just slightly above a fraction of a few degrees compared to up to 4 degrees Celsius by the end of the century is quite significant. And so we also see that climate change is not projected to be uniform across the globe. And so again, here we have this lowest emissions scenario in comparison to the highest emissions scenario. But in both cases, we see that where these colors are indicating the temperature change expected by the end of the century, it's not uniform across the globe. So this is not all just one color. And specifically, we have the highest amounts of warming taking place at these higher latitudes. We also have specific regions in Africa, in South America, throughout Asia, and throughout North America that all are warming more rapidly than others. And so you might be looking at these graphs and you say, okay, well, I see that's quite different, and it's very clear that different projections are going to tell us different things about what the world might look like at the end of the century. But I only see that there's a couple degrees difference. And so, when I wake up in the morning versus when it's 3 p.m. and the sun is brightly shining, I feel like the weather is a few degrees different. So what's the big deal if we warm that much? One of the keys here is that there's a lot of effects on extreme events, even if we shift the temperatures just by a couple degrees on average. And so this is really important to my work on extreme events. And so here, this looks like a complicated graph, but it's quite simple once we break it down. So I'll try to do my best in doing that. So we have essentially a range of temperatures. So we have cold up to hot, and the probability of occurrence. So how likely are these temperatures to occur? And so we'll look at this first curve, which is sort of the climate that we're in today. And so we see that the average climate, or the average temperatures, occur most often. And so that's why they're highest on the graph. And so we have these very rare cold events, which are very low on the graph, and we have these very rare warm events, which are very low on the graph. If we were to shift this whole graph to the right by increasing the average temperatures on our planet by just a few degrees, what we see is that if we're at the same exact temperature threshold, so say this is 100 degrees Fahrenheit, whereas this curve was quite low in the previous climate, in this new shifted climate, we're at a much higher probability. And so the likelihood of surpassing 100 degrees Fahrenheit or even higher becomes a lot more likely. And specifically, we have this occurrence now of things that we rarely ever saw. So temperatures like we didn't even see in previous climates now become our new record events and the things that we look as being extremes. And so that when we use this language of being that we're creating a new normal through climate change, this is kind of the types of calculations that we're thinking about. This idea that things that were really rare previously now become more and more likely with the influence of climate change. And so this is really a combination of the change between climate change and climate variability. So naturally, there's going to be very rare events and very likely events, but as we change our climate, we're going to see that those impacts are very significant. And so an example of this is the Lucifer heat wave that was observed in Europe in 2017. So temperatures throughout Europe surpassed 104 degrees Fahrenheit. We saw a 15% increase in Italy's hospital admissions, and they were linked to the starting of wildfires throughout Portugal. And so people wanted to know, how likely would these events have been without the impacts of climate change? So if we had gone backwards in time and hadn't emitted all of these greenhouse gases versus what they are today. And what the studies were able to show is that the maximum observed temperatures during this heat wave were 500 times more likely due to climate change than they would have been without. So I think this is a really powerful example where these very rare events can become much more likely with just a couple degrees additional warming. Other impacts include things like precipitation. And so precipitation has a variety of different complex controls, including how easy it is to evaporate water off the ocean, changing wind patterns, et cetera. But these graphs kind of indicate that our changing climate not only depends on region, but also on seasonality. And so we see in the United States, throughout the summer months, we have an overall drying effect. So these brown colors are indicating that there's less precipitation, while these blue colors are indicating that there's more precipitation. But in the winter months, we might expect that there's actually going to be some regions in the northern United States that get more precipitations, while the southern half continues to be more dry. And so those kind of differences are really important to note as well. Another example of impacts that you might have been hearing quite a lot about in the media is discussions of sea level rise. And so sea level rise can occur as climate changes for two main reasons. And so the first is that we have a lot of ice that's on land. And as that ice melts, it'll flood into the oceans. And that's going to increase the amount of volume that's in our oceans. And the second is through this process that we call thermal expansion. And this is just the idea that as things warm up, the molecules move around a lot faster and they take up a lot more space. And so that's happening to our ocean as well. As it increases in temperature, it's going to take up more space. And so what we can see, I think these are really powerful images from Climate Central, are these artistic depictions of what the world's going to look like under a 2 degrees Celsius warming scenario and a 4 degrees Celsius warming scenario. So you can see here on Miami Beach at just a 2 degrees Celsius warming scenario, we have really devastating sea level rise. And so a lot of these coastal buildings and these homes are going to be in a flooded zone. And if we increase the amount of warming up to 4 degrees Celsius, this is even more dramatic. Similarly, we can look at the same kinds of images for New York City. And so this is like a famous sculpture of the bull down in the financial district. At a 2 degrees Celsius warming threshold, we're at a very different region of the United States, and we don't see that much of a change. But if we're at 4 degrees Celsius, the amount of sea level rise becomes really jarring. And so I think like this really demonstrates the difference in the impacts of these two different trajectories. And so that can be kind of daunting. You know, those images are quite striking, and I'm bringing us back to a similar curve that we saw for temperature, but now for sea level rise. And I think that the key is that these trajectories are not set in stone. We are not headed on this 4 degrees Celsius temperature increase and the associated sea level rise that goes with it. And so what can we do to achieve the safest pathway possible? The biggest thing that we really need to do is to cut emissions. And so there is some additional warming that's baked in associated with how long essentially greenhouse gases hang out in our atmosphere, but the rest is really within our control. And so the things that we need to focus on are shifting the way our electricity is produced. So the more that we can use renewable energy, the better. And then once that's changed, this really allows for really great innovation in transportation. And so the use of more hybrid and electric vehicles is really beneficial, particularly when our energy is produced in a more sustainable and a more green manner. And then another example is even just producing our agriculture more efficiently. And so these, our little cow friends, as you may know, are a very large source of methane in our atmosphere, which is another greenhouse gas we talked about previously. And so making sure that we're raising livestock and producing agriculture in the most efficient way possible is really beneficial to cutting emissions. The second pathway is really to actively remove carbon from our atmosphere. And so all of these sort of warming targets that we make for ourselves are really essential. Most of them require that we do some kind of carbon renewal. And the easiest way to think about this is simply that we can plant trees. And so reforestation and land management, you know, as these trees are doing photosynthesis, they're taking in CO2 from our atmosphere. And it's a very easy and direct way of taking CO2 that would be detrimental for our climate. Similarly, we have a lot of propositions about geoengineering, which are more industrial or scientific ways of reducing carbon in our atmosphere. But they're really, I won't get into them. We can talk more in the questions portion if people are interested, but they can be very costly. And there's a lot that's still not known about sort of negative impacts of geoengineering as well. And so there's really no silver bullets. The third thing that we need to think about is adaptation. And so we don't want to throw anything away and say like everything's inevitable. We just need to adapt to the way our climate's going to look in the future. But we really need to understand that our climate has already changed. You know, we've seen how dramatically temperatures have increased throughout this presentation and the impacts that has on our communities. And specifically, this is going to impact specific communities who are already struggling, who are already disproportionately affected by socioeconomic challenges, much more than they are other communities around the globe. And so these types of interventions involve industrial construction, so things like barriers that prevent river flooding, as well as enhancing adaptive capacity, so reducing poverty around the world, providing additional education resources so that communities are more autonomous in the ways that they can adapt, as well as developing robust adaptation plans. So here's an example of the amount of states in the United States that have types of adaptation plans associated with climate change. And so as we move into the future, having more of those and having them be more robust is even more essential. So in conclusion, we've taken sort of a long journey through Earth's climate history and its future over today. But what we've seen overall is that the climate really has changed throughout Earth's history, but the rate at which it's warming today is really unprecedented. And so the likelihood of extreme events has already changed in recent decades, and we can really expect that to continue if we continue to expose our atmosphere to additional greenhouse gases. But as we look towards the future, our warming trajectory really isn't set in stone. And so there's urgent action needed for both mitigation and adaptation if we're to ensure sort of essential, safe conditions in both the short and long term. So I'll stop there, and I'm happy to answer any questions that might have come up. So thank you again for letting me present today.
Okay. That was wonderful. Thank you, Casey. That was a quick, very thorough, accessible tour. Thanks so much. So I'd love to open it up to questions for Casey. Feel free to put any questions or comments in the chat, or if you're comfortable turning on your cameras, if you want to just raise your hand and ask a question, please feel free to do so now. Victoria?
Hi, thank you, Casey, so much for this presentation. You know, in talking about the changes, does this have to be done on a worldwide, you know, of all countries, everybody's in, of course, to make a bigger impact, and of the industrial countries leading the way? Is that correct in saying?
Yeah, I think that's a really great point. I think that this is a really great question in terms of thinking about where the impacts occur and who's causing them. And so specifically, there's a very disproportionate amount of our greenhouse gas emissions coming from very large countries. So the United States is definitely one of the biggest culprits of greenhouse gas emissions, both today and throughout the history of this country. And other very large countries such as China also have very large amounts of emissions. And it's important to think about too, like how large these countries are in comparison. So if we're to scale the amount of emissions to the amount of people that are living in those countries, that sort of presents a new way that we can measure who's churning out the most greenhouse gases. And so if we are to make the best impact in terms of reducing climate change and preventing all of these impacts, it really does need to be a global effort. But the countries who are the biggest culprits really need to be the leaders because they're the ones who are going to have the most impact. And so I think it's really interesting, especially when we think about sea level rise. We saw how dramatic that could be in Florida, but we also think about these very small island nations across the globe who are feeling the impacts of climate change, but they're not contributing nearly as much as these huge global economies are. And so I think it definitely needs to be a global effort in order to reach these most stringent targets where everything is as safe as possible. But the biggest culprits need to be, I think, the leaders in those changes.
Thank you.
Yeah. Other questions? Let's see. Okay, I have a question from Deborah. Casey, since I have 5 young granddaughters, what are 3 things that they can do to combat climate change?
I think that's a great question. Yeah, so one of my favorite, I spent a lot of time doing research at my time at the Environmental Defense Fund, looking at agricultural production. And so one of the biggest things, as we saw in this presentation, is that cows produce a lot of greenhouse gases. And so if they want to take one effort, I would definitely recommend reducing meat and dairy consumption. And that can just be something as easy as doing meatless Mondays. It can be the choice to swap out one meal a day that's vegetarian or that doesn't use dairy products. And that's something that's, I think, pretty attainable. You know, you don't have to convert to vegan overnight, but if you can make one swap towards that goal, it can feel really powerful. Another thing I think is the way that we use transportation. And so anytime that they can ride their bikes instead of taking a car, or they can make sure to carpool, that's something that's definitely within your grasp. And then things, you know, like they may have heard, but making sure to turn off the light switches at night to just conserve energy wherever necessary has really big impacts, not only on the amount of greenhouse gases that we're reducing through energy usage, but also, you know, it's beneficial for your family if you want to cut down on your electricity bill. And so there's a lot of like co-benefits to a lot of these changes. Beyond those, I guess, really concrete examples, I would say the best thing that they can do is to talk about it. And so a lot of the biggest change that occurs happens at sort of a policy level. And so the best thing you can do is stay educated and make sure you're talking about it with people who may have very different beliefs than you do, and really engage people as much as possible. And so if they're young enough to know that the climate is important to protect, I think that it sounds like they're very smart and they have a really great grasp on the science. So it's great to practice those conversation skills as well.
Very good. Question from June. Will Tesla change the world with the clean energy? How about pollution generated during the battery manufacturing?
Yeah, this is a great question as well. I think this is definitely one of the trade-offs. I don't know the exact sort of cost benefit of the emissions that are associated with building these types of machines and these types of cars. But the key is really that if we are to rely more on electric vehicles, once our electricity becomes clean, this reduces a lot of different emissions. And so essentially, if we're able to currently use our electric vehicles, it's my understanding that the amount of emissions coming from those vehicles today is still reduced in comparison to your typical automobile. But if the electricity that's coming from, or that's fueling those cars essentially, is coming from wind energy or it's coming from solar energy, that's sort of a doubled effect on the amount of emissions reductions that we can see from those kinds of changes. And so those really do have potential to have a large impact in the future.
Questions? Casey, what is the general tone like with you and your community at Columbia and beyond? Are you feeling overwhelmed or a little bit hopeful or just kind of energetic?
Yeah, I think overall it can be a tough space to work in all the time and to look at these numbers all the time. But I think at least what I tend to think about is we saw in this presentation, but in general, that the Earth is really powerful. And it has these very strong cycles that it goes through all the time, and it will regenerate, and it'll, it takes a lot to be able to change Earth's climate. And so I think that that's really a statement on the power of humans to change the world around them. And so even though we've made some negative impacts on our planet, I think that really indicates how much power we still have to flip the scene and to make impact in a positive way now. And so I think that that's, while we have, a lot of frustration dealing with these kinds of problems every day, I think we also get to see how quickly the solutions and the progress gets made, and that can be really empowering as well.
It's good news for us.
Yeah.
Another question from June. Is there any data to predict, basically, I guess, the life of the Earth, the lifespan of the Earth, especially if we keep going in this direction?
Yeah, I think what pops into my mind as the closest example would be sort of calculations that we can do to, there's this concept called like the runaway greenhouse effect. And so there's this idea that we have what's called a positive feedback in terms of the impacts associated with climate change. So if the Earth gets hotter, it's easier to evaporate water into the atmosphere because as you can think of the way that your body sweats to cool yourself off, the same thing's happening with evaporation as the temperature increases. And so the more water vapor we put into the atmosphere, water vapor, we remember, is also a greenhouse gas. So that's going to warm the temperature of the planet. And so this cycle can kind of continue on and on and on, in theory, until we run out of water on our planet. And luckily, we've done calculations that have been able to show that the amount of time that would take is much longer than how much fossil fuels we really have to burn. And so luckily that doesn't seem like necessarily a very plausible example. But other things, and what my research looks at is sort of when are we going to cross these thresholds at which humans can survive? And so specifically with humid heat, there's very specific temperature thresholds at which our bodies can't sweat anymore. So if it's really, I'm sure we've all felt that feeling. I lived in New Jersey for 4 years, so I know New Jersey summer can be really humid, and you feel how hard it is to sweat when it gets really hot and humid outside. And so there's a point at which your body just can't cool itself anymore. And so as the climate continues to change, we're going to expect to see more and more instances where those temperatures occur naturally on our planet. And so that's going to necessitate things like air conditioning in places that don't necessarily have really good access to these kinds of things, or their electricity grid can't support it for everyone. And so I think those are the kinds of questions, perhaps a little less literal in terms of the life of the planet, but how long we can expect to survive comfortably on the planet.
Question for Lori. Thank you for such a clear and concise explanation of climate change. Will changes made on a town and statewide level have much effect?
Yeah, that's a great question. I think they do. I think if anything, they provide really wonderful examples of how organizing and how advocating for your own community can have a really big impact. And so another thing that I study is very local effects of humid heat or extreme heat. And what we see is that there's really big differences in the amount of temperature rise that might occur in a specific city versus like a rural area right outside the city. And this has to do with things like the amount of concrete that's there, the amount of paved roads that are there. And those are things that we have direct control over at a very local level. So you can plant more trees, which are going to increase the shaded area and make it more comfortable for citizens to be outside. And those kinds of changes are going to have direct impacts on the everyday lives of citizens. And so I don't think that those are very trivial changes. I think they're very powerful. And in terms of inspiring more global or country level change, I think that often they draw a lot of attention and that they can really set the stage for greater change as well.
And actually, Joanna, I don't know if this might be a good time for you to mention your website, Sustainable Ridgewood, just in talking about the the town-wide effort.
Sorry. Hi there. Sorry. Sustainable Ridgewood is basically a hub of sustainable information for the community, and largely the content is driven by the community. So I myself, wanting to raise my 4 kids in a more sustainable way, and very aware of the amount of energy that we contribute as a family and the amount of waste that we generate. I was just interested to find out, what we can do as a family, and furthermore, like what we can do as a community. And so I started looking into it, and the information was fragmented. And so what I'm hoping is to sort of consolidate all that information for the community so that we can all learn together how to live a more sustainable life.
Wonderful. And we're going to be, we can share the website, with this routing list in December or January. So, I'll be sure to do that once it's up and running.
Great.
And I like that you said you're doing this as a family. I know with different family members that I'm spending more time with now, they're all vegetarians, most are vegan. So just being around them, cooking for them, I have kind of lost my, I'm eating a lot less meat now, and I don't have the feeling for it as well. So just knowing it's really for such a good cause, when you're making sacrifices, whether it's transportation or food or whatever, it's just nice when you're doing it with people who are like-minded. So I think that's wonderful. Victoria has a question. Do you see any positive trends from corporations to change or realize their impact?
Yeah, I think we definitely do. I think it's too slow. Like, I would love for more of them to take faster action, but I think it's really becoming clear to a lot of corporations that this is what people want, is they want sustainability, they want to live on a safe planet. And if anything, if it's not motivated by like the moral good of their company, they know that it's not sustainable for them to continue to produce in the way that they do and not take into account environmental considerations. And so really in terms of economics and who's going to support their brands and their companies, I think that more and more organizations and more corporations are starting to see that they need to take these things into account to really be viable.
Mm-hmm. You have any other questions, comments? Okay. Louise, did you want to tell us about the little bit about the observatory?
Yes. Hi, everybody. Thank you, Katie. That was great. That really summed up in a big picture what's going on, which is very hard to understand sometimes because you get so many mixed messages from the media, and depending on who you listen to, one friend will say one thing, another friend will say another thing, and you never know what to believe. But I started working at the Lamont Doherty Earth Observatory in January this year, and I am not a scientist. I'm just a mum of 3 boys, and I have learned so much since I've been there. But what has amazed me is the just this, the Lamont Doherty Observatory is in my backyard. It is literally 20 minutes from my house, and I'd never heard of it before. It was established in 1949, and it is a leader in earth sciences in the world. It is part of Columbia University's Earth Institute, and there's around 200 PhD level researchers working and teaching there, studying the planet from its deepest interior to its outer reaches. And they're looking at ice cores, tree rings, sediment cores. They're coming up with evidence on global warming. They're coming up with solutions. And I think the most exciting thing that's happened since I've been there is Lee Bollinger, the president of Columbia University, announced at the United Nations in July in front of heads of universities from all over the world that Columbia would be launching a climate school. And what they're going to do is integrate the whole of Columbia into this. So it's not just Lamont Doherty that's looking at it. It's not just the Earth Institute that's looking at it. It's bringing in the business, every single area of expertise at Columbia is going to be involved in the new climate school. And I just find that so exciting that an institution like Columbia University, this is the first new school they've announced in 25 years, that they are launching a new school, and they are going to be looking at this. And I just find that really exciting. And I'm not a scientist, but I think climate change is staring us in the face at every turn we take, and it's scary, but it reassures me to know that something is being done about it. So, and Roberta, can people see the chat? If I
Yes.
post a couple of links. Okay.
Yes, absolutely. Please do.
The information about the climate school, and I'm also going to share the sign up for our newsletter, because we have a monthly newsletter that comes out, and it's a summary of all the research that's going on, what everybody's looking into. And I just think it's just sign up for the newsletter, read about it every month, and realize that if we all do our bit, then it really does make a difference.
Yeah.
Thank you for hosting this sustainable series.
Wonderful. So please take a look at the link that Louise just put in the chat. And as Lori mentioned in her comment, that she has followed many of the live streamed lectures, and they're phenomenal. I've gone to one or two, and I plan to do more. And then we're going to be working together to get some speakers from the panels. So I think it's really exciting. So thank you for that. And we have one more question. We have Pamela, who's a village council member and somebody who we're so thankful in Ridgewood is very passionate about environmental issues. And let's see, Pamela's question is there a cause and effect relationship between climate change and coronavirus?
Yeah, that's a super complex question. There are some interesting, I think, interactions between the two. So specifically, we saw there's some interesting studies out there that have looked at the dip in emissions that occurred when everyone kind of went into the first lockdown. And so, as I'm sure most of us experienced, we weren't going in cars very often. No one was flying very often. And so that was a pretty significant decrease. But it turns out because industrial production and so many other controls are influencing climate change so significantly, even if we lived all of our lives like that, it wouldn't have sort of the necessary change that would prevent us from some of these large climate impacts. So that was something that was pretty surprising to me, that even those big changes in the amount of emissions weren't perhaps as significant as I would have expected. Perhaps another example that we were talking a lot about this summer was sort of the impacts of climate change and how that might make the spread of coronavirus worse. And so things like people's access to cooling centers, if temperatures are really hot in the summer and they might not have air conditioning at home, people will typically, go to a mall or go to these specific cooling centers in the public that provide them with free air conditioning. And so given that we were in this lockdown and people might not have access to those public centers to get that air conditioning, it sort of encourages more people to get together in these small groups that could increase the transmission. And so the interplay between a lot of these different issues is something that's really important.
Any other questions or comments? Well, let's see. Oh yeah, Michelle mentioned that the Lamont newsletter is definitely worth signing up for. It's amazing. And as Barb said in the chat, this information, Casey, you presented tonight, very easily digestible information. It's extraordinary the amount of information you have right here. I mean, it's incredibly thoughtful, intelligent presentation. And I just want to thank you on behalf of all of us just for your time and just, just presenting what can be very difficult concepts in a very accessible way, and your energy and your excitement about finding hope in all of this and making sure we all find a way to make sacrifices and get excited about turning things around. It's just, hopefully it's contagious in a good way. So just thank you so much. And we hope to have you come back.
Yeah, I would love that.
Before we got on, we were talking about the documentary about Greta Thunberg that's coming up this year. And I might get a little climate panel together. So that would be a really exciting time to have you come back and join us. And our next speaker on Wednesday, December 2nd is on our call right here, Welchud Unger, and she'll be talking about hydroponic gardening. So it's a way to grow incredibly organic veggies and fruits all during the winter and the early spring. So we're excited to have you coming next month. So thank you to each and every one of you for spending time with us tonight on this really incredibly important topic. And Casey, thank you so much. I hope we see you soon.
Yeah, thank you so much for having me.
Okay, all right. Good night, everyone. Thank you. Thank you, Louise. Thank you, Joanna.